All right, so there have been a couple of equations in undergrad and grad school that whenever like the teacher is written it out, I'm like, what the heck do you even do with this? Like, this is not useful. And if it is, you have to spend a ton of time freaking using it before it's even useful. So there's two equations. The first one is conservation of momentum. Let's do conservation of mass first. The other one is also COM, so I did conservation of mass, but now it looks weird, but I don't care. dm dt. All right. You're like, what do I even do with this? What does half this stuff mean? And I didn't know either, but I spent time figuring it out, and here it is. So this term is the most complicated one. You can pretty much always bring the dv. You can integrate it and bring it outside. So you can rewrite it as d dt of density volume. And then now you have to do the chain rule. So you get d rho dt. We get v d rho dt plus rho dv dt. All right, and I'll talk about what that means in a second, but that's a simplification. This term is basically just m dot. But what does this part mean? So if you have, like, let's say this is your control volume. The surface is the surface of the control volume. So let's say you have a velocity pointed that way. Your normal is also pointed that way. Your normal is always perpendicular to the surface. So up here it's pointed that way. If you have a surface that looks like that, it would look, that would be the normal. That would be the normal. Oh. That would be the normal. It's always perpendicular to the surface. So if this is your normal, this is v, 100% of v is pointed in the normal direction. So in this case, v dot n just equals v. But if you had same control surface and you had v pointed, I'm gonna make it more exaggerated, v pointed in that direction, your normal is still pointing in that direction. So now you only have part of the velocity pointing in the normal direction. So that's theta. So v dot n would equal v should be cosine of theta, because at 0 degrees, it's 1. 90 degrees, it's 0. Yeah. And to be honest, same over here. Over here would be cos theta, but theta is 0, which means it's just v. So you can kind of rewrite it as v cos theta, if that's your angle, or v sine theta if you want to use that angle. But yeah, either one's fine. So, and you can pretty much always bring the dA out front. You can integrate the dA. So you're left with a rho v cosine theta. Now, what does this simplify down to? This simplifies down to m dot. That's because A has units of meter squared, rho has units of kilogram, meter cubed, and V is meter per second. So that cancels out, and you're left with kilogram per second. So this is m dot times cosine. That's literally what it boils down to. And the last term is dm dt. That's the rate of change of mass in the control volume, but that is effectively this term. So it's kind of double counting. So you always kind of just say that's 0. So you're left with 0 equals v d rho dt. This is volume, by the way, not velocity. I know there's 2 v's and it's confusing. Plus rho d volume over dt plus m dot cosine theta. Okay, so what does this mean? Well, let's look at an example. I'm not going to do one with numbers. I'm just going to do it theoretically. So let's say you have a balloon. So you have a balloon and someone's blowing into it. Let's not even say someone's blowing into it because I don't want to use air because air is compressible. Let's say someone's blowing into it with an m dot and it's water. So it's incompressible, which is nice, and you'll see why in a second. And our control volume is the whole balloon. And it'll grow over time because the balloon expands. So in this equation, what can we do? So density with time is 0 because we're putting in water, and water is incompressible. If we were blowing in air like normal people do, that wouldn't be 0, and then this would be a more complicated equation. But I'm gonna say you're filling it up with water, so that way I can cancel out that term. Then, what about the second term, the dv dt? That is changing because the balloon is expanding. The volume is expanding with time. And last term, m dot cosine. Cosine is m dot cosine. That is 1 because right here, the normal is pointing outwards. Technically, it's -1 because it's going in the opposite direction. But yeah. Cool, so what are we left with? We are left with 0 equals, oh wow, density dv dt minus m dot. So then we rearrange and we get dv dt equals m dot over density, and then v equals m dot density times time plus a. What is that a? It should be that v at t equals 0 equals a v naught. So the balloon initially has a volume before you even start blowing water into it. So then it would be t equals 0, it's 0. So a equals v naught. So then it would be v equals dot over rho t plus v naught. There you go. And it's v as a function of time. So that's how you use this equation. And again, this is the simplified version of the equation. And it is very nice. Because like, you're gonna spend half the time on a test solving this problem just understanding what this equation even is. And just skip that, just rewrite it as this all the time. Technically, this is like a sum of m dot, because let's say the balloon had a second opening like over here. and some mass was leaving, but let's say it's like m dot over 2 mass was leaving, then you'd have to count for that also. But yeah, that's the first equation, conservation of mass. Very cool. The second equation, conservation of momentum. And that is m dv dt equals dt I'm gonna rewrite this a different way. Okay, there you go. That is a conservation of momentum. So what is this term? This term is m dv dt. dv dt is a, it's acceleration. So it's ma, and that is force. What is this term? This is... All right, let's assume you can bring dv dt out of the integral again. So it'll be d dt v density volume. That'll be... Okay, so that'll be dv dt and that'll be that's kind of messy. This is the change in velocity with respect to time. This is the change in density with respect to time. This is the change in volume with respect to time. So it's a little messy, but that's what those terms mean. And for the example I'm going to show later, you can cancel them all out anyways. This term, but if you don't cancel them out all, if you don't cancel all of them out, it'll be the same process as up here, like with a balloon. Cool. So this term, v dot n, is just v cosine theta. We went over that up here. This term is what is that term? That is let's assume you can bring the a out of the integral. VPA. Yep. And that is, this should be m dot also. Yeah, that's what we showed up here as well. That's also m dot. So this is m dot v times cosine. And this is momentum. Pretty cool. So, final form, force equals I'm gonna say it's the sum of those. Okay. Now there's a surprise term in here that I don't yet, well, let's see actually. Okay, pressure shows up in here somewhere. I don't want to think about it right now, but I think one of these three comes out to pressure times area, because there is that term in there. Okay, so an example problem. Let's say, where's a good place to write it? I guess right over here. Let's say that you have a box. Let's say you're shooting in water, so it's incompressible. Shooting it in there, it's going through a channel, then being shot out down there. Likewise, you're shooting in water here, it's going through a channel and being shot out here. And let's say this has a m dot, a v, pressure, and area. And same here, and same here, and same here. So what would you do? Change in velocity with respect to time, we're going to assume that's 0. Because let's assume the m dot, don't need velocity because that is m dot. Let's assume it's steady state, so that term would go away, the dv dt. Then density with respect to time, also 0 because incompressible, because I'm picking water. If it was air, then that term wouldn't be 0. And change in volume with respect to time is also 0, because this is just a freaking box. It's not a balloon that's expanding, it's just a box. So we're left with F equals sum of m dot v cosine plus, I'm going to add the term here, sum of pressure times area. This is the final form that you care about. So this equation boils down to that. And this equation, yeah, boils down to that one. Okay. So what are you going to have? You're going to have, let's look at the m dot v. Well, okay, you do need the v actually because it's m dot v. So you're going to be shooting in momentum here, and you're going to be shooting it out here. And you're going to be shooting this in there and shooting it out there. And there's also a pressure acting on that surface. There's a pressure pushing that way, and a pressure pushing that way, and a pressure pushing that way. Now, this was like almost an exam problem that I had a while ago, and it's just a lot of algebra, but it's all very doable. But yeah, that's basically the equation. And it's pretty neat that you can boil this stuff down to this. Same with conservation of mass. Cool beans.